Hello, everyone. We are Group 10. Today, I'll be presenting a summary of the key trends in medical computer vision, based on a synthesis of recent survey papers published between 2022 and 2024. This is a field that's constantly evolving to meet the increasing demands of modern medicine. Introduction. In the age of precision medicine and digital healthcare, computer vision, or CV, is a crucial technology for automating the analysis of medical images. It helps with a wide range of clinical tasks, including diagnosis support, monitoring disease progression, and treatment planning. CV applications are already being used in many clinical workflows. For example, they're used for tumor segmentation in MRI, CT, and ultrasound images, and for predicting metastasis or recurrence from histopathological data. They also play a role in removing artifacts and enhancing images from low-dose devices like CBCT and X-ray. 3 major trends. Medical computer vision faces unique challenges, such as the high demand for accuracy and the scarcity of labeled data. Our analysis identified 3 major research trends addressing these challenges. Trend 1. Problem specialization. The first trend is a shift from general-purpose tasks to clinically specific problems. Historically, the field focused on broad tasks like classification and segmentation. Now, the research is more grounded in solving specific clinical needs, such as artifact reduction for different noise types in CBCT scans, tumor localization in ultrasound images, patient-specific structural delineation for treatment planning. For example, one review on breast tumor segmentation structured its analysis around clinically relevant tasks like ROI delineation and boundary estimation, rather than just general segmentation. Trend 2. Data efficiency. The second trend tackles the key bottleneck of high-quality annotated data. Labeling 3D medical images is very expensive because it requires a lot of time and expert effort. To get around this, researchers are turning to more data-efficient methods like semi-supervised learning, which uses a small amount of labeled data and a large amount of unlabeled data to train models. Generative models such as GANs and CycleGNS, which can synthesize new data, including synthetic CT images. Transfer learning, which leverages knowledge from models trained on large, general datasets like ImageNet to improve performance on new, data-scarce medical tasks. Trend 3. Practical constraints. The third trend emphasizes that modern models must be more than just accurate, they need to be practical for real-world use. This means a focus on interpretability, providing insights and not functioning as a black box. Generalizability, ensuring models are robust to domain shifts, like different hospitals or scanner types. Deployability, creating models that are efficient and have low latency for use in clinical environments. This includes research into things like uncertainty quantification, domain generalization, and creating lightweight models through techniques like knowledge distillation. Trend analysis, paradigm and architecture. This table highlights key architectures and paradigms in medical computer vision. UNet is a foundational architecture for segmentation, using an encoder-decoder CNN with skip connections to preserve detail and context. Generative adversarial networks, GANs, and CycleGNS are used for generating data and are relevant for artifact reduction and segmentation. Transfer learning addresses data scarcity by leveraging knowledge from large, pre-trained models to improve performance on new medical tasks. Semi-supervised learning alleviates the annotation burden by using a combination of labeled and unlabeled data. Transformers capture long-range dependencies, overcoming the limitations of CNNs, and show potential for breakthroughs in medical imaging. Lastly, federated learning enables training across multiple institutions without sharing raw patient data, ensuring patient privacy. Conclusion and future directions. In conclusion, medical computer vision is undergoing a transformation. Success is no longer measured by just technical novelty or benchmark scores, but by clinical relevance and real-world viability. Looking ahead, several promising directions are emerging. Cross-center generalization using techniques like federated learning to ensure patient privacy while training on diverse data from multiple institutions. More annotation-efficient methods, including active learning and weak supervision. Hybrid architectures that combine the strengths of CNNs and transformers. A strong emphasis on model transparency and trustworthiness to gain regulatory approval and clinician trust. The future lies in interdisciplinary collaboration between researchers, medical professionals, and regulatory experts to build AI systems that are not only intelligent but also interpretable, reliable, and truly impactful in clinical practice. Here are the list of papers for your reference. Thank you for listening. Any questions is appreciated.